Okay, happy day everybody. So here's what we're going to do right now. We're going to be taking a look at the Unit 11 stuff for acid base. So this is going to be, some of this you're going to see is still going to be a repeat of what we did in Unit 2. So some of it still is review. There really isn't a ton of stuff that's new. There's a little bit on buffers, and yes, buffers are going to be really important, and so that's what we're going to be talking about today. So you can see that the first page of the notes is going to be talking about, like, what is a buffer, okay? And then we're going to talk about those reactions, again, of acids and bases where we get neutralization reactions and what happens when you have a neutralization reaction. So we'll talk a little bit about that, hopefully, today. The second part is calculating what is called using the Henderson-Hasselbalch equation. How do you calculate the pH of a buffer solution? So one, what does it mean to have a buffer? Two, how do you calculate the pH of a buffer? Okay, and very similar to what we've been doing, but this Henderson-Hasselbalch equation is really a shortcut to it. Okay, so we'll do a little bit of that. Then the third page of the notes is on titration curves. We've already started talking about titration curves, but making sure that you can see, like, if you're given a curve, can you figure some stuff out about the curve? And so there are some details on the curve. This problem down here, we already did. How do you calculate the pH when you're in the middle of a titration? We said there were 4 steps to doing that. Let's see if you remember what the 4 steps are. Let's try not to look. Step number 1, you need to use Mervet equals Mervet to figure out moles. Step 2, subtract to find the excess. Very good. Step 3, divide by the new total volume. Very good. Divide by the new total volume. Step 4, negative log it. Awesome. Negative log it. If it's the OH minus was an excess, you just found POH. And then if it's, so that's what this part is down here. So again, like I said, some of this is going to be a review of what we've already done. And then the last page is also a little bit more specific on, like, what happens in a titration curve. What are some of these? Sometimes you can have like a polyprotic acid. What is a titration curve? Look for something like that. So that's basically it. That's where we're going in this last part of the unit. All right, so let's go back right up to the beginning here on the buffer notes. Okay. So first thing is, what is a buffer? Okay. So anytime that you have a buffered solution, like the best example of a buffered solution is blood, okay? What does your blood naturally do? It maintains a constant what? pH. Awesome, okay? So it says buffers are solutions prepared to maintain a nearly constant pH. That's the definition of it. It is that easy. It's pretty amazing. It really is pretty incredible, because what your body naturally does is, once your levels are off just a little bit, your body has its way of naturally coming back to whatever its equilibrium point is, okay? So it'll throw in different ions that you naturally have, and so you can get more of a particular ion. If your body can't naturally do it, then you're going to need some type of medication to be able to get that to happen, okay? And so that you can have something that is called acidosis, which probably means what? Yeah, high acid levels, okay? And so there are different terms, but, something that's called alkaline, it means what? Versus something that's acidic. Alkaline just means it's more basic, okay? So it says the solutions are designed to consume any excess H plus or OH minus, and it naturally does this. That's what a buffered solution does. For example, human blood is a buffered complex medium with a pH about, anybody see what our pH is roughly? 7.4. It's about 7.4 is normal. Any variation in pH can result in death. And so if we look up here, you can see that if you have like acidosis, you can have your normal pH, your alkalosis, or it can also be death if it gets above like 7.8. So around 7.4 is going to be our normal pH. Now, you're looking at this though, and what are you probably thinking? Is acidosis actually acidic? No, it's just what? It's a lower pH from what normal is, okay? So just keeping those types of things in mind too, because sometimes people will think that that means that it's actually like less than 7, but they're just saying that it's lower than what it's supposed to be. So buffer solutions resist a change in pH because they have different parts of either an acid or a base that they can kick out, and then it'll absorb either too much acid or absorb too much base and just neutralize. Generally, they'll contain a weak acid in its salt. This is really important. I want you to like box this in, highlight something, something, a weak acid in its salt, or I also want you to box this one in the same way, or a weak base in its salts. Okay, everybody, if it's an acidic buffer, everybody's going to repeat after me. It's made of a weak acid and its salt. If it's a basic buffer, it's made of a weak base and its salt. If it's an acidic buffer, it's made of weak acid and its salt. If it's a basic buffer, it's made of weak base and its salt. Don't forget that. That's huge for buffers, okay? It's probably one of the biggest things about a buffer. So, HF is a weak acid. Do you remember what the strong acids are? Iclobber, no, 3-chlor-4-so-4, okay? So those are the strong acids. That's weak, and that's called its salt, okay? And the reason why it's called its salt is the anion is exactly the same. Notice that they both have F in them, okay? But it's a salt because it's going to start with one of the alkali metals, okay? Weak bases. What are the strong bases? You know the strong ones are all of the 1As and Caserba. Perfect. That's not one of them, so that's a weak base. What makes this its salt? Well, now the beginning part, if it's a base, the beginning part is going to be the same. So the NH3 is actually inside of the NH4, okay? And then you're going to have the rest of it, which in this case is the HCl. So just keep in mind, as you do these calculations with buffered solutions, these are merely solutions with weak acids or bases, and the procedures for solving the problems are going to be the same. Does anybody remember what, so they're giving us the equation for Kw, and they're saying that it's equal to Ka times Kb. K of the acid, of the weak acid, and Kb of the base. If it has a K, it's weak, okay? So these must be weak. Anybody remember what Kw is equal to? It's called the ion product constant for water, but what is it actually equal to? Good! 1 times 10 to the negative 14. Does it have units? Nope, K does not have units. And what is that equal to? What's the equation for it? H plus times OH minus. And again, don't forget, this is actually H3O plus. It's actually hydronium, but we can use H plus for that. If the Kb is larger than the Ka, what ion do you think they're saying is predominant? There are other words that they can use for that too, but what ion do you think is going to be showing up more? If the Kb is larger than the Ka, then the OH minus must be bigger. Okay, then it must be more basic. Okay, if the Ka is larger, then it must be your H plus ion is predominant in the solution. Okay. Usually the following is true. Acid plus base usually gives you what two things? Water and salt. And I always like to say Walter and Saul are a couple of buddies that always walk into your local deli. So the acid and base are going to give us water and salt. Okay. You can see here in the reaction where it's double dating. We talked about this before. My H and my OH are going to go together. Actually, I think it's easiest to just say my H and my Na are going to switch places. Okay? And so it's like same thing down here. My Na and my H, my positives are going to switch places. We get a double dating reaction. And now it's neutralized. Okay? So this we would say is neutralized on this side. Okay. And if it's a strong acid, strong base, we would expect that the pH equals 7, and we would call it, should give you a neutral solution with the pH equal to 7. Okay, so we're going to talk about that now. So if it's a strong acid and a strong base, we should get a neutral solution. If it's a strong acid with a weak base, what type of solution do you think we should get? Take a guess. Very good. It should be more acidic. If your acid is stronger, it should be more acidic, okay, when it's neutralized. So these are just a couple of examples. What if it's a weak acid and a strong base? Now your solution at the neutralization point should be more basic. And again, what does that mean? So if it's acidic, we said that our pH should be less than or greater than 7. Less than 7. But if it's basic, our pH should be greater than 7 when it's neutralized, okay? So it will be neutralized, but then greater than or less than. If it's a weak acid plus a weak base, it depends on the substances. It depends on their concentrations. I'm just going to say on the substances. So you can't tell. If one of them is strong, you can tell. If both of them are strong, you can tell. If they're both weak, it's inconclusive. You need to be able to see and be able to calculate it and do it with numbers in order to figure that out. Okay? I don't know why I have that. Depends on something. I said it depends on it again. Okay, so let's figure this out. Here's how weird this is going to be. The question's going to say something like, which of the following is acidic? Or which of the following is basic? What's wrong with looking at these and having A, B, C, D as your options, or A, B, C as your options? And I said, which of the following is an acid? What's wrong? None of them are an acid, okay? But if I say which one will be an acidic solution, what we're going to do is something, this is my shortcut, okay? This is usually not taught this way, but this is my shortcut. I want you to put an H up here, and I want you to put an OH up here. Because what it's going to do is, this is going to be your salt, and the salt and the water are going to react with each other. That's what are your products from your acid-base reaction. And what we're going to do is I'm actually going to basically crisscross these. And when I crisscross these, what acid do you get? HBr. Is HBr strong or weak? Strong. I'm going to write strong acid in parentheses right after it. What base are we going to get? LiOH. Strong or weak? Strong. It's one of the 1As. Lithium is one of the 1As. When you react a strong acid and a strong base, what do you expect it to be? Neutral. Awesome. Okay, let's try the next one. So I'm going to put my little H and my OH, and you can kind of do, and obviously it's acetate. That's your acetate ion. So what are we going to get as our acid? Which is called? Acetic acid. Very good. We have acetic acid. Strong or weak? Is it one of our iclobber, no 3-col-4-sulfur? No, it's weak. Plus, what's our base? RBOH. This is one of the 1As. It's an alkali metal, so strong or weak? Strong. Okay, on the count of 3. Oh, oops. I just wrote A instead of B. On the count of 3, acid, base, or neutral. 1, 2, 3, go. Basic. Very good. Because your base is stronger, that's going to be basic. Okay, NH4NO2. So obviously we're going to have our break right there. I have HOH. Okay. Let's do our acid first. What's the acid? HNO2. That's called, not nitric acid, nitrous acid. Strong or weak? Weak. Nitric would be strong. NO3 would be strong, but NO2 is weak. And what's our base? NH4OH. That's called? What is that called? Ammonium hydroxide. Ammonium hydroxide, by the way, is just ammonia, okay? So, strong or weak? What are our strong acids? Say it again. 1A and Caserba. Is that part of them? No, it's not. That's weak. So, acid, base, or neutral? We don't know. This is going to be question mark. Okay? We don't know on that one. That's a question mark. All right? In each case below, indicate which salt will form the more acidic 0.1 molar solution. So what you're going to do here is you're basically going to do the HOH and the HOH over here. Okay? Now what I want you to do is I just want you to figure out if it's going to be acidic or basic or neutral. Acidic, basic, or neutral. So you don't have to write them all out. Okay? So in your head, you're going to do this so that it's a lot faster. What acid do you have in NaNO3? HNO3. Strong or weak? Strong. What base do you have? NaOH. Strong or weak? Strong. So you have 2 strongs, which means this should be neutral. Just write an N for neutral there. Okay, now let's do that same thing to this one. What acid are we getting? HNO3, strong or weak? Strong. What base are we getting? FeOH3, strong or weak? Weak. So if it's a strong acid with a weak base, what do we expect? That it's an acid. So this one must be more acidic. That one must be more acidic. You see how that works? Okay. So go ahead. Let's have you try B, C, and D, and let's see how we do. Let's review these. Okay, so what did we get for KBr? Acid, base, or neutral? Neutral. Very good. They're both strong. What did you get for KBRO? Acid, base, or neutral? Basic, because KOH is a strong base, but HBRO is going to be weak. So which one's more acidic? The KBr. Okay, when they say more acidic, they're just saying it has a lower pH. Okay. All right, in letter C, acid, base, or neutral on this top one? Yeah, I would agree. Acid. It looks like a weak base, but HCl is going to make a strong acid. So I would say acid on that one. BaCl2? Neutral. Very good, because BaOH2 and HCl are both strong, so that would be neutral. So which one's more acidic? The one on the left. Okay. NH4NO2, acid, base, or neutral? You don't know. NH4NO3, acid, base, or neutral? More acidic. So if that one's definitely more acidic, if I had to guess, and it has to be one of the answers, I would go with that one. Okay, I would probably go with the one that's definitely more acidic. Okay, so the last thing for today is we're going to memorize the Henderson-Hasselbalch equation. Okay, so we're going to say it a couple of times just to get it down, and I kind of have like a little bit of a rhyme to it. So what I say is pH equals pKa plus log of Cb over A. Okay, ready? We're going to say it together. We're going to say it a bunch of times, and then we're going to try pKb, okay? Or POH, sorry. Okay, here we go. Ready? pH equals pKa plus log of Cb over A. Say it again. pH equals pKa plus log of Cb over A. Now, you are going to be given the equation, okay? But it is one of those things, and if you end up eventually becoming a physician, I've had people tell me this, they remember the Henderson-Hasselbalch because of this, okay? Ready? Here we go again. pH equals pKa plus log of Cb over A. One more time. pH equals pKa plus log of Cb over A. Okay, let's try POH. Let's see if we can figure it out. POH equals pKb plus log of Ca over B. Do you see how that goes? Okay, let's do pH again. Let's go back to pH. I just wanted you to see how POH you could figure out if it's a base. Okay, ready? pH equals pKa plus log of Cb over A. Last time, try not to look. pH equals pKa plus log of Cb over A. Awesome. Okay, that's all we're doing for today. Happy day, everybody. And I will talk to you guys or get you an email soon.